Okay, so thank you to the organizers for giving me the opportunity to speak in such a beautiful place. Is it? Hello? It's just not close enough. Oh God, I keep having this problem. Hello? Is this loud enough? Okay, everyone can hear me. Okay. Okay, so thank you. And today I'm going to be talking about a recent paper I have out with my supervisor, Tim Adamo, on the KLT kernel in twistor space. So kind of the point of this paper, there's some delay, okay. The kind of point of this paper was to connect two different ways of organizing scattering amplitudes at tree level. So my entire talk will just be about tree level scattering amplitudes. And one way that we can kind of organize these amplitudes is via the double copy. So this relates gravitational amplitudes to gauge theory amplitudes. And another way that we can organize them is in terms of the external helicity configuration of our amplitude. So that's like the MHV sectors. So let me just go through some basic properties of these two things. So the double copy, I'll just be talking about the KLT double copy, but there's a lot of different variants at this point. And the KLT double copy was kind of the first one, and it was discovered in 1986 and relates closed and open string amplitudes by basically gluing together open string amplitudes using monodromy relations into some closed string amplitudes. And then taking the field theory limit of this amounts to saying that an endpoint tree level gravitational amplitude is equal to some sum over two copies of gauge theory amplitudes organized by some color ordering and glued together using something that we call the momentum kernel or the KLT kernel. And in principle, you can use two different bases for these kinds of decompositions, but they have to be size n-3 factorial. So. And something very cool about this KLT kernel is, let's say we take a basis like this. So then you can write it in this form where what I mean by this sum is that we sum over all Mandelstam variables so that I is less than j in both the orderings alpha and beta. So if alpha was 4, 5 and beta was 5, 4, then we would, then for example, 4 would just be less, no, 3 would just be less than 4. Okay. Is this somewhat clear? I don't know if I can put it in words. I can write something on the board, maybe? Okay. So let's say we have S 1, 2, 3, 4, 5, and 2, 1, 3, 4, 5. So this is our beta. This is our alpha, sorry. And this is our beta. And then the KLT kernel for this is we basically go through this product. So firstly, for j equals 4, we have that here in this ordering, 3 is less than 4. And here also, oh, this is quite trivial actually. Okay. And here also 3 is less than 4. So we can have S3, 4. And we can't have anything else because 5 is not less than 4 in this ordering, even though it is here. And now we can look at 5. Here we can see that 5 is greater than 4 and 3. But here, 5 is only greater than 3. So we can only actually have S3, 5. So this is the KLT kernel for this color ordering, for example. So if you evaluate these for all of the color orderings in your bases and view it as a matrix over these bases of color orderings, then if we calculate the matrix inverse of this, this is actually related to binary tree graphs that are planar with respect to both of these orderings. Okay? In the following way. So here BT I will denote as like the binary trees that are planar with respect to those orderings. And then we have these, basically these propagator products over this particular tree. So as an example, so this is just one element, but imagine we have all of the others and we take the matrix inverse of this, then S minus 1, 2, 1, 3, 4, 5, 2, 1, 3, 5, 4. This up to a sign is just equal to minus 2, 1, 3, 4, 5. So this is the Feynman diagram that corresponds to this color ordering. And these are actually the amplitudes in bi-adjoint scalar theory. Which, yeah. Basically just cubic vertices, only cubic vertices. Yeah, that's how I'm going to treat it. Okay. So this is actually amplitudes in bi-adjoint scalar theory with this Lagrangian, where we're considering a massless scalar valued in the adjoint representation of two possibly different Lie algebras with a cubic vertex. And then amplitudes can just be expanded in terms of like a doubly color ordered partial amplitudes like this, and we have these kinds of amplitudes, for example. This is one example. Okay, so this is some key properties of the KLT double copy that I want you to remember. Very closely related to bi-adjoint scalar theory, and we have this KLT kernel that we can build. Okay. Next, I want to talk about helicity configurations. So as we all know, the simplest scattering amplitudes at all multiplicity are MHV amplitudes at tree level. And we know that the Park-Taylor formula is just a single term for any n. And for gravity, we also have a similar expression known as the Hodges formula, which has quite a long history of different constructions. But I'm going to stick to the Hodges formula, which basically gives the gravitational tree level scattering amplitude as the reduced determinant of a certain matrix that I'll be defining later. Okay, so why are MHV amplitudes so simple? You can argue this using supersymmetry or using like the number of ways you can contract polarizations with momenta, but I think kind of the most beautiful way is to argue using integrability, which basically the simplicity I'd say comes from the integrability of the self-dual sector of both of these theories of Yang-Mills and gravity. And we can view the positive helicity particles from earlier as a self-dual background. So these are all self-dual particles, so we can view them as a self-dual background. And a powerful tool we can use when we have self-dual theories is that twistor theory trivializes these in gravity and Yang-Mills. And here I've just given a quick definition of twistor space as an open subset of CP3. And then self-dual backgrounds can be encoded by deforming the complex structure on twistor space or introducing a holomorphic vector bundle over twistor space. But I'm not going to go into detail on these things. So, is this gonna work? Yeah. So we can now view our negative helicity particles as perturbations on this background, and then derive our MHV amplitudes as two-point correlation functions on a self-dual background. So here, just view all of these positive helicity particles as background. And then this you can also view as a helicity flip amplitude on this self-dual background. And we can also extend this using various methods to describe scattering on non-perturbative self-dual backgrounds, such as radiative, self-dual Taub-Nut, and self-dual Dion backgrounds. And generic helicity, so beyond MHV, can be derived using twistor string theory. And you can prove these using BCFW recursion. So these are given by the RSVW formula for Yang-Mills. I'll be explaining all of these elements later on. But the key point is that this Park-Taylor term looks very similar to the usual Park-Taylor MHV formula. It's just that we have some different product here. And for gravity, we have the Kachazo-Skinner formula, which is now given in terms of two of these reduced determinants integrated over something that I'll explain later. And all of our external kinematics are encoded in these things, which you don't have to worry about this for now. But yeah. So these formulae at d equals 1, they just reduce to the Park-Taylor formula and Hodge's formula. But as we increase the helicity, they start growing in complexity, and like it starts being harder and harder to calculate what they are. But in some way, they encode like the complexity of how many diagrams we actually need to calculate these amplitudes. So just another slide on, in some way, how to generalize from MHV to the D minus MHV. So we just add some, we just change these and integrate over something. Okay. So what this talk is about is we have a double copy structure that takes us from Yang-Mills amplitudes to GR amplitudes. At the same time, we have some helicity grading of these amplitudes, which basically encodes the overall simplicity, or like at MHV, it's just one term, for example. And we have explicit representations of these formulae in terms of these integrands integrated over some space, some moduli space. So the question that I'll be answering in this talk is the final arrow in this diagram. So what is the explicit relation between these two representations of Yang-Mills and GR amplitudes? And then I'll be talking about some of the consequences of this relation. Is that kind of clear? Okay. So I'm going to talk about, going to explain more about these amplitude formulae that I glossed over earlier. Then I'll look at some applications of graph theory that we can use on these to find a double copy at the level of these integrands. Then I'll talk about some aspects of this new form of the double copy, and then I'll end with a conclusion and outlook. Okay. So this might be a bit dry, but hopefully you can stick with me. So I'll just be going through every element of this kind of formula. So this is the general form of our amplitudes. So we consider maps of degree D. So in this measure, like here, we consider maps of degree D that go from CP1 to twistor space. What I mean by degree D is that if you look at the scaling with respect to the projective parameter on CP1, then these maps goes R to the D, or equivalently, you can encode them in terms of a polynomial, like if you're on this patch, a degree D polynomial. And so since this lives in CP3, this polynomial has 4 times D plus 1 degrees of freedom up to the projective scaling on CP3. And then additionally to this, so we integrate over these moduli of the maps, and we also integrate over the locations of punctures, of n punctures corresponding to the external particles on this Riemann sphere. And we're left with this kind of object. So we're modding out by all of the redundancies here and integrating over the moduli space of maps. The external kinematics are encoded in these objects here, which are Penrose transforms of the momentum eigenstates of our external particles. The Penrose transform states that solutions to the zero rest mass equations on space-time can be thought of as cohomology classes in twistor space, and we choose, for momentum eigenstates, we can choose this representative, for example, where this is our map, and these ki's, kappa i's are our external momenta written in spinor helicity variables. Okay. So something interesting to think about is like, what does this actually localize to? What does this actually integrate to? So these are just the integral over the moduli space of maps and our external kinematics. And in fact, this object forces our integral to entirely localize on a set of solutions, and then 4 delta functions which encode the 4 momentum conservation. So some way to see this is that we have these 2d plus 1 moduli in mu, which appear here in this exponential. So if we do this integral, we pick up 2d plus 2 delta functions, which then cancel, which then localize all of the other integrals up to 4 delta functions. And as an example, at d equals 1, this just entirely localizes this integral to one solution, and this corresponds to the Park-Taylor formula. At higher degree, this integral localizes to this number of solutions, where these are the Eulerian numbers, and they satisfy that the sum over all possible helicity configurations, so d is n to the d minus 1 MHV. If you sum up all of these, then you get n minus 3 factorial. And if anyone knows anything about scattering equations, these are the number of scattering equations that we have for tree-level scattering, and these are known as the refined scattering equations that these satisfy. Okay, so, and this number grows kind of as we violate helicity and then go back down again. So, okay. So now let's have a look at these integrands. So we're going to need these two objects. So this is known as the Vandermonde determinant of a set A of the marked points. And we use an inner product, the natural inner product on CP1 for these points here. And Yang-Mills, the integrand here, for a certain color ordering rho, which I've kind of denoted as the circle here, is given by this object, which should remind you of the, which is a Park-Taylor factor in terms of these normal brackets. So hopefully that's okay. And for gravity, we have these two reduced determinants, which I'll go more into detail. Okay, so these are determinants of, so the first one is the Hodges matrix, which have these entries. So we have the off diagonals, which are given by this, and then we have a relation for the diagonal entries of this matrix. Dual Hodges matrix, which is this one, is similar, and it's over the negative helicity gravitons, which I denote like this. This one is over positive helicity gravitons. And again, we have a relation between the off diagonals and the diagonal elements. So what this means is that if you were to evaluate the determinant of either of these matrices, they actually have a zero eigenvector because we have a relation between the elements. So in order to find a non-zero quantity, we need to define these reduced determinants, which basically amounts to removing one row and one column from each of these matrices, and then in order to, and then dividing by a certain Vandermonde determinant. And in fact, these are independent of which row and which column we remove. Okay, so is that kind of clear, like how these are defined? It's okay. Well, we'll go more into detail later. So the question that I posed earlier is really, how do we relate these two integrands of these two theories? And for that, I'm going to go into the world of some simple graph theory. So I'm sure everyone is familiar with tree graphs. These are just a set of edges over some set of vertices V that is connected and has no loops. So for example, this is a tree graph. Now, it's possible to associate some weight wij with each of these possible edges that we have in this tree graph. So I've assigned some here. And then we can kind of assign a total weight to each tree by multiplying all of these weights together, which is kind of this object here. And now a very cool identity is that if we sum over all possible tree graphs on a set of vertices, so if we sum over all possible tree graphs you can build out of connections between these vertices, weighted by these weights that I've assigned to them, then this is equal to the determinant of the weighted Laplacian matrix, where we've removed one row and one column. So this should be ringing some alarm bells from 3 slides ago, because we just saw an object just like this. And in fact, I mean, part of the original derivation of this object was kind of like this. But we can actually rewrite our Hodges reduced determinants in this language as a prefactor and then a sum over trees spanning, for example, the positive Felicity gravitons with some associated weight in this way. And we can also do this for the dual Hodges matrix. So for dual Hodges matrix, we have a prefactor, and then this should be there. And then a sum over trees spanning the negative Felicity gravitons, weighted by some matrix that I haven't written down here. Okay, so we've turned our determinants into trees. Now, Yang-Mills is associated with orderings. And we can actually associate orderings to trees. But this requires that we assign to each tree graph a root. So here, this is the tree graph from earlier. I can give it a root, for example, 8 here. And this gives a unique direction to each of the edges in this tree graph, like this. And we can now associate a set of orderings to each of these trees as kind of orderings compatible with them. So hopefully these 2 examples will give the overall intuition of how these are defined. So this tree has a single associated ordering because there's a relation between each of the edges next to another. So B is before 1, is before 2, and it's all concrete. On the other hand, this tree has 2 different orderings that we can associate with it because 1 and 2 don't have a relation. So we don't have a set ordering, so we can assign B12 and B21 to this tree. And now we can associate products very similar to what we saw before for our determinants. So we have this 1 over ij, which you might have spotted earlier. We can associate this kind of product for each tree rooted at B to a sum over compatible orderings like this of Park-Taylor factors in this way, for some generic X in CP1, which basically just soaks up some weights. Okay, so now we can relate ordered trees to orderings. So let's do that. Okay, yes. This just follows from yeah. Yeah, exactly. But okay, let's apply this to our trees. So let's select a single tree in this sum. So I've done something sneaky here and I've just oriented our tree, but this is okay because all of our weights are symmetric, so it doesn't really matter in which direction we're going. So I've rooted our tree at B. And now let's look at each of these trees, products of weights. So from the start, this is equal to this product here. And now I will just keep pulling out 1 over ij's using the previous proposition which then turn into Park-Taylors. So doing this once, we get this kind of object, and doing this again, at the cost of introducing this ij here, we get another Park-Taylor factor. Okay, so this is looking good because Yang-Mills was related to these Park-Taylor factors, and we now have two. It's great. So our weighted tree has turned into Park-Taylor squared times something else. Okay. So now let's do the sum over these weighted trees that I was talking about earlier. So we have a sum over trees spanning the positive Felicity gravitons for this Hodge's determinant, and then a sum over all orderings compatible with this tree, and then these Park-Taylor factors. But these are finite sums, so we can actually just swap summation. So we can sum over all possible orderings, and then sum over all trees compatible with those orderings with the same factor here. And completing this calculation, we basically find that our reduced determinant is equal to some Park-Taylor factors times something else, which is constructed out of these like square brackets and some other contractions of things on CP1. And we can repeat the same thing for the other determinant, which is over the negative Felicity gravitons. So we can glue together these two contributions from det H and det HV, and we find that our gravity integrand can equivalently be written in this form, where this is the object that we call the KLT kernel in twistor space. And these are basically the integrands for Yang-Mills. And this is the definition of this KLT kernel. So here is where I've put all of these somethings that I was mentioning earlier. And we have a prefactor which only depends on this ordering and not the other one. And these are the weights on each of these trees. And here, this notation means that we're considering all trees that are compatible with the orderings rho, tilde, and omega tilde. Okay. So another way of looking at it, we have this prefactor, and then we have a sum over trees. One of them is on the negative Felicity gravitons, and one of them is on the positive Felicity gravitons. Now, if you don't like trees, if you don't like this, then you can also view this as this sum, which we saw earlier. So this is exactly the sum that I was trying to work out here of pairs that are less than each other in both orderings. So trees or this, whatever you want. Okay. So with this, we found a representation or a connection between these two theories at the level of integrands using something, using this KLT kernel. And this is inherently Helicity graded because the sum over orderings, if you recall, one of the orderings was over negative Felicity particles and the other one was over positive Felicity particles. And also the different contributions, these phi ij's, are different according to which tree we're summing over. So it's kind of weird. Okay, so just want to say, we've completed the diagram. Let's see, there, okay. Now, let's look at some kind of aspects of this structure. So first of all, what are we summing over? How big is it? What are we integrating over? So this is a matrix on orderings of the positive Felicity gravitons and the negative Felicity gravitons. So this basis here has size n minus d minus 2 factorial times d factorial, which is graded by the helicity of the external configurations for the amplitude that we're considering. But So KLT had n-3 factorial basis elements, for example. But we kind of have to make up for this by summing over these solutions to the refined scattering equations, which are given by these Eulerian numbers. And these are pretty big, or can get pretty big. Notably, when d equals 1, this just reduces to the usual KLT kernel. So this is kind of so if you know CHY, like how the double copy works in CHY, there we have a basis of just one element, because you can basically divide your integrands. But we're summing over n-3 factorial solutions. And as I said, in KLT, we have a basis of size n-3 factorial. So this is in some way a bit different. It's kind of in between these two extremes. Okay, so as I mentioned right at the very start, if you remember, the KLT kernel, the field theory KLT kernel, has this really beautiful property of, if you invert the matrix with respect to the color orderings, then you get another theory called bi-adjoint scalar theory. And so something very nice that we would want, that would be really nice to have, is that this object here, if we inverted this matrix and integrated it in some way to soak up the weights with some scalar wave function representatives, does this also make sense as an object? Can we say anything about this? And so this is, in principle, it's quite difficult to invert a matrix like this. I mean, this has a huge, like very quickly growing basis. Like the dimension of this matrix is very big in general, but it does have this structure. So this you can just view as a diagonal matrix multiplying everything, this prefactor. And then we have these two objects over these ordering compatible trees, which look very similar, if you remember, to the usual field theory KLT kernel. And in fact, we can use this result. So this is basically saying the inverse of KLT kernels are bi-adjoint scalar amplitudes. We can use this result, which basically amounts to what I was saying earlier with this, but now with generic weights. So now we don't have to have Mandelstam variables anymore. This works for any symmetric weights Wij. So we don't need to use any properties of Mandelstam variables or momentum conservation. This just works. So we can use this formula to this theorem, that the inverse of this is equal to these binary trees, to invert each of these elements separately. So that gives us the inverse of this object here, given by 1 over this prefactor, and then a sum over all binary trees that are compatible with both orderings, in this sense here, weighted by these phi's that I've not talked very much about. But you can view these basically as kind of propagators. So they're summed up in these diagrams. Okay, so this is the inverse. And another way of viewing this is as some binary trees over the negative Felicity gravitons and some binary trees over the positive Felicity gravitons. And then in this paper, we proved using BCFW recursion. Yeah. Yeah. So if you remember these orderings, so any tilted ordering is over just the negative Felicity gravitons, and any non-tilde is over positive Felicity gravitons. And then you have this weird permutation of A and B. So here A and B are not next to each other, and here they are. This basically means that the only bi-adjoint scalar amplitudes that we're allowed to consider on the left-hand side are those where, this is quite fun to work out, but are those where you always have a partition into a set, into these two sets. So you have this. Yeah. I mean, what kind of, I basically mean the type of color orderings we can have here. Yeah, it's just color orderings. So that's going to be my next point, basically. Yeah. So the only bijoint scalar amplitudes that we can describe at degree D, like degree D from this formula, are those where the two sides, so these are the originally positive Felicity particles, and these are the originally negative Felicity particles, where they're always disconnected. Well, they're always just connected by a single propagator. So this is imposed by the form of the color ordering we have. Plus minus. Yeah. Yeah. Mm. Yeah, so all of these, and there's a single term, so you must have this propagator connecting the positive Felicity to the negative Felicity. Okay, so yeah, so you can prove that this holds. I mean, this statement isn't really that revolutionary because basically you have a sum over trees like this, which is equal to the integral over a sum over trees that look the same. But it's cool that it works, that this object, which we got from the integrands, actually satisfies this. So, and this kind of gives a natural sense of helicity violating degree to these doubly color ordered bijoint scalar amplitudes. And so something I'm working on now is applying these kinds of ideas to Yang-Mills scalar. And it turns out that a very similar structure also exists there, where you can basically expand this in different helicity sectors according to the color orderings of the scalars and the helicities of the gauge theory particles. Okay. Well, how am I on time? Okay, it's fine. So all of the story was in flat space. So yeah. Mm, I don't. I haven't had time to think about this like very deeply, but I'm not sure. Maybe. Yeah. Maybe you have more thoughts than me. So. Okay. So all of this was on flat space, but I gave a hint earlier that you can also extend some of these formulae to self-dual tube backgrounds, basically. So a general question that one may pose is we have all of these very nice properties of amplitudes in flat space, but to what extent do they depend on the flatness of the like classical solutions that we're kind of expanding around? And can we generalize some of these statements to more general backgrounds? So you can define, for example, amplitudes using various methods like the perturbana method, on like using Lagrangians where fields have some background value. So this is just a vague statement of this. And one question that you can ask is whether there's a notion of double copy on these for these amplitudes. So some of this has already been explored at 3 points on plane wave backgrounds by this group here. And it suggests that some structure like this might exist. So there's many different configurations that you can, like it's not quite clear whether we should look at Yang-Mills on a gravitational background, Yang-Mills on a colored background, some combination of this. So still not quite sure exactly how it could work. But I'll be considering some Yang-Mills amplitudes on a Yang-Mills background that can maybe see if they double copy into something on a gravitational background. Okay, but the 3 points, which has been done, it's not a very high multiplicity. It doesn't give us very much data in how this could actually work. So, so we can make use of some all multiplicity formulae that you can derive using twistor theory on self-dual backgrounds given by these two. So you don't have to think very much about what's actually going on here. The key components are that this is an amplitude on a Cartan valued radiative self-dual background. And the key element here is that we have Park-Taylor, this Park-Taylor factor again. And the gravitational amplitude, which is also on a radiative self-dual gravitational background, has very similar components to the flat space one in terms of these reduced determinants of matrices like Hodge's matrix, and then some operators acting on them. So because we see these very similar structures, you can just apply the same story that I was talking about before to these amplitudes. And you can find something. So you can write this as this, if you want. Summing over some bases of orderings, and you find an object here. This looks somewhat similar to before. So in the flat space limit, it just reduces to the same thing. But it now has more general coefficients. So we can't make use of this really nice inversion theorem that I was talking about before. And these matrices are huge for general numbers. So it's hard to invert and simplify them into anything that makes sense. So it's hard to interpret these kinds of things. And also whether this is even the right kind of double copy, because maybe we need to double copy something on a gravitational background into gravity. I don't know. So this is something I've been thinking about. Yeah. So these are basically insertions of the News tensor of this radiative field. So the data that we're throwing in at Scry to determine this field. And then we have the sum over T's, which are basically like the tails, the gravitational tails coming from this background. Yeah. But overall, all of these are essentially just bigger versions, but they basically extend Hodge's matrix a little bit. So you can apply the same thing again. I mean, at 3 points, this is it's not. Well, I mean, here what you can see is you actually need to conjugate. So in that double copy, you had to conjugate one of the Yang-Mills amplitudes. You had to change the color charge. And you also have to do this here to get anything that makes sense. But yeah, that's the only thing I can say. Yes. Oh, okay. I'm pretty much done. So anyway, this is, yeah, I'm not sure what to say about this, but it's a direction. Okay. So that's actually me pretty much done. So what we found is a new double copy structure between gravity and Yang-Mills tree amplitudes that is labeled by helicity. And this is naturally manifested in twistor space as a KLT kernel integrand. And integrating this inverse gives us color-ordered biojoint amplitudes. And now some further directions that I'm interested in are, can you extend this to other theories? So there exists, for example, Einstein-Yang-Mills formulae in twistor space. Could you, like this would basically be a consistency check for this type of double copy, whether we can construct some other theories like this. Is there anything more concrete that we can say about double copy on curved backgrounds using what I showed earlier? And lastly, some more like conjectural things, like does there exist some twistor string origin for this structure? Does it come from intersection theory in some way, like a lot of other KLT double copy things do? These kinds of things. And with that, I'd like to thank you. Yeah.
Hi, thanks for that very nice talk. I think Song had a kind of what I might call a naive biojoint scalar formula in twistor space, which was simply to divide through by the multiply by a second Park-Taylor and divide through by determinants. Does that relate nicely to this?
I think this is by Cachazo, like the scalar blocks, minimal basis of scalar blocks, or
I think it just had two Park-Taylors, but then you had to divide through by the Hodge determinants, which
So you can also try to do that. You can do Park-Taylor, divide by the other integrand. And see. But so the thing with this formula is that it has a lot of spurious poles because you divide by this.
Yeah, it looked really naive.
Determinant. Yeah. So you need to sum up a lot of these. So this is kind of cool. But you need to sum up over all of the different helicity configurations in order to actually get the biojoint scalar amplitude. So each particular helicity sector is not equal to a biojoint scalar amplitude, like for this formula. I would say, yeah. Yeah.
Do we have any other questions? Thanks for that. I hope this is not a super boring question.
Fine.
But it looked like the rhos and the omegas kind of play an asymmetric role. Is there some reason you choose that particular basis of Park-Taylors on the rho side and omega side?
So do you mean this prefactor, basically?
David's telling me that's a very boring question.
So you mean on this prefactor? Or
well, you've chosen a basis to write your S matrix. I'm just wondering, is that because it's the best basis or some other reason?
So this basis is basically, so this is actually different to what I was writing before, but it's essentially the same idea. So yeah, maybe we can talk about it afterwards, but basically this guarantees these two orderings guarantee that you have only these amplitudes. So you need to choose this to get the right representation. And it's, yeah. I mean, we need to consider all orderings here. Like we can't restrict anything at the moment. Yeah. It's basically you apply KLT to both sides and then you get gravity. But
I don't want to bore everyone.
Yeah, so maybe we could talk about it.
I'm not bored, but yeah.
Yeah.
I've got my own questions, but I think I'm happy to ask you over coffee. So let's thank Sonja for a fantastic talk.